All right, here we go with trigonometry. Incredibly important stuff for you to go into further mathematics classes, especially honors pre-calc. In honors pre-calc in the fall, it's going to be assumed that you have certain facts memorized, that you know the sine, cosine, tangent of a 30-degree angle, a 45-degree angle, a 60-degree angle, 90-degree angle, etc., all the way around the unit circle. So memorization will be key. It's very, very important that you hold on to the notes that you're going to take in this unit and have them available for next year. Do not throw these notes away. All right? So, in this textbook, we glean information from 3 different chapters when we learn about trigonometry, but we don't do a lot of information. We don't do a lot of assignments out of the book. It'll be mainly stuff that I created. So, that's what we're going to be doing. We're going to start with a little review of the basics of trigonometry, talking about SOH-TOA relationships. Okay? So, the 3 main functions are sine, cosine, and tangent. The symbol there is called theta. Cosine or sine of theta, cosine of theta, tangent of theta. Theta is just a variable. It could be x, it could be whatever. But many times mathematicians, for whatever reason, have used Greek letters to represent angle measures when they're talking about variables. So you'll see theta, you'll see alpha, beta, whatever, okay? So don't get freaked out by that, it's just a variable. All right, let's review one other thing. We have a diagram of a right triangle. The 2 sides of the triangle that make up the right angle are called the legs. Okay, these are the legs of this right triangle. This is the hypotenuse opposite the right angle. This triangle is labeled triangle ABC based on the capital letters at the vertices. One conventional thing that we do is we typically call this side opposite angle A. We call it side A, but we use a lowercase letter for that. So this side would be side B, opposite angle B, and this would be side C. Just to get that out of the way, we're going to talk about that more throughout the unit. But for this one, we are given 2 of the sides. And anytime we know 2 of the sides, we can find the third of a right triangle by using the Pythagorean theorem. We know that a squared plus b squared equals c squared. Or in this case, a squared plus 8 squared equals 17 squared. Well, 8 squared is 64. 17 squared is 289. If you subtract 64 from both sides, you get a squared equals 225. And the square root of that would be a positive or negative 15, but only the positive one makes sense this time. And we get a is 15. This side down here is 15. Now, you might remember from previous classes Pythagorean triples. And one of the Pythagorean triples that we learned is 8, 15, 17. So if you remember your Pythagorean triples, that's just a shortcut, and it saves you the time from doing this. That's much like all the shortcuts we're going to learn, all the things I'm going to ask you to memorize are going to be shortcuts for you to save time every time we're dealing with trigonometry. So that's why it's important to memorize some things. But 8, 15, 17. Now, in any right triangle, the sine of an angle is the ratio of the opposite leg compared to the hypotenuse. That's where SO comes from. Sine, S, opposite is O, hypotenuse is H. CA is cosine, is adjacent over hypotenuse, and tangent is opposite over adjacent. That's where TOA comes from. Now, relative to an angle, if I'm looking at angle A, the adjacent leg is the one that helps make up that angle. It's attached to it, so the 8 would be adjacent to angle A. The 15 is opposite, across from angle A, and the hypotenuse never changes. It's always opposite the right angle. Relative to angle B, though, the opposite leg would be the 8, the adjacent leg would be the 15, hypotenuse is still 17. So let's fill this out. The sine of angle A, sine is opposite over hypotenuse, would be 15 seventeenths. The sine of angle B, opposite over hypotenuse, would be 8 seventeenths. The cosine of angle B would be adjacent over hypotenuse, that'd be 15 seventeenths. We are already given that the cosine of angle A is 8 seventeenths, you can see why. The tangent of angle A is opposite over adjacent, that's 15 over 8. And the tangent of angle B, relative to angle B, is opposite over adjacent, that's 8/15. Some things here I want you to notice. The sine of angle A is equal to the cosine of angle B. If A and B are the acute angles of a right triangle, this will always be the case. The sine of one of those angles will equal the cosine of the other, and it happened here too. That's not a coincidence. That'll always be the case. And the tangent of one of the acute angles is the reciprocal of the tangent of the other acute angle. So those relationships will always be there. So there's just a basic, reintroduction of SOH. Now, the new thing for a lot of us is this thing called radian measure. The further you go in mathematics, the more you measure angles in radians and the less you measure them in degrees. So it's important to get a grasp of this. Radian measure, it's just a different way of measuring an angle. Just like we have different units we can measure temperature in, we have different ways we can measure angles. So, right now, if I asked you to picture a 60-degree angle, you could probably have a pretty good idea of what that looks like in your mind. But you probably don't know what it means to say, if I ask you to picture a 2 radian angle, you wouldn't know what that looks like. Hopefully, you'll get a sense for that though, okay? So here's what it means. Here's central angle X. It's a central angle, which means the vertex is at the center of the circle. Here's the radius, R, and this is the arc length between these 2 points, S. It's the length of that arc. That's marked as S. The way you measure an angle in radians is you divide the arc length, S, by the radius, R. That's how you measure an angle in radians. So, if you have an arc length that's equal to the length of the radius, which is pretty close to the case here, then you've gone through 1 radian, because S divided by R would be 1. All right? Now, here's the important thing. If you increase angle X to 360 degrees, meaning starting here at 0, going all the way around, that'd be a 360-degree angle, would be a full circle. That means the arc length would be the circumference of the circle. And we know that the circumference of the circle is given by the formula 2 pi r. So, if you wanted to measure the angle in radians, if it was a 360-degree angle, in this case then, to calculate S divided by R, it'd be the circumference of the circle, which is 2 pi r divided by r, and the r's just cancel, and you get 2 pi radians. So therefore, 360 degrees is equivalent to 2 pi radians. If you divide both sides by 2 of that equation, you get a radian equivalent. Pi radians is equivalent to 180 degrees. This is the staple that I want you to know first and foremost. 180 degrees is equivalent to pi radians. Okay? And pi, of course, is just 3.14159, blah, 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 blah. But we're just going to keep it in terms of pi. So in terms of pi, let's complete this table of radian equivalents. 90 degrees would be equivalent to what? Well, if 180 degrees is pi radians, 90 degrees is half of that. So that'd be pi over 2. Okay? And then we already know that 180 degrees is pi radians. 270 degrees, well, we could relate it back to 90. 90 times 3 is 270. So if 90 is pi over 2, 270 is 3 times pi over 2, or we just call it 3 pi over 2. And 360 is twice as much as pi, or is twice as much as 180, so that'd be 2 pi. Okay? And this is one family. These are organized in a very helpful way. These columns are going to be important to memorize and really study. Okay? The next column is a 45-degree family. Let me change colors here so we have an obvious difference. Okay. In a 45-degree family, 45 degrees is 1/2 of 90, or 1/4 of 180. Maybe we want to think of it that way. 45 goes into 180 4 times, so it's 1/4 of 180. So in radians, that'd be pi over 4. 135 degrees, That's not as obvious, but it's 3 times as much as 45. If you multiply 45 times 3, you get 135. So if 45 is pi over 4, 135 is 3 pi over 4. 225 degrees is 5 times as much as 45, so that'd be 5 times pi over 4. Always relating it back to the top one. And 315 is 7 times as much as 45. So if 45 is pi over 4, 315 would be 7 pi over 4. And that's your 45 degree family, or pi over 4 family. Notice that in radians, everything in that column ends in pi over 4. That's important. 30 degrees. 30 degrees is 1/6 of 180. So if 180 is pi, 30 degrees is pi over 6. 150 is 5 times as much as 30. So if we know what 30 is, just multiply it by 5, we get 5 pi over 6. 210 is 7 times as much as 30, so that'd be 7 pi over 6. 330 is 11 times 30, so that'd be 11 pi over 6. And there is our 30 degree family, or pi over 6 family. Everything there ends in pi over 6. And finally, the 60 degree family. 60 degrees is 1/3 of 180, so that'd be pi over 3. 120 is double that, so it'd be 2 pi over 3. 240 is 4 times 60, so that'd be 4 pi over 3. And 300 is 5 times 60, so that'd be 5 pi over 3. So the first assessment is going to be just dealing with SOH-TOA relationships and radian measure and knowing these. And I want you to try to memorize these, okay? And that will be our first lesson right there.